Hello, this is Vikas from IARE College. I'm from Data Science Department, C section. The topic I'm going to discuss is about a fast algorithm for joint eigenvalue decomposition of real matrices. Let's start our topic with the introduction first. Let's consider a joint. Let's for the first point is we consider the joint eigenvalue decomposition (JEVD), also called as joint diagonalization by similarity. The principle of JEVD is to diagonalize a set of k non-defective matrices as the following way. For all k is equals to 1 to k, m power k is equals to ad power k A inverse, where the matrix of eigenvectors A and the k diagonal matrices dk are unknown. We only consider here the real cases for simplicity. Note that the matrix of eigenvectors A is estimated up to permutation and scaling indent. This limitation is inherent to JEVD problem. The uniqueness condition of the JEVD problem is given in the given matrix. Let the n into n by k matrix be be the matrix whose columns are the diagonals of each matrix dk. JEVD is unique if and only if the rows of the matrix are all distinct. The JEVD is useful in several contexts. The number one, direction of arrival estimation. The second point, joint angle delay estimation. The third point, multi-dimensional harmonic retrieval. Fourth point, canonical polydiac decomposition of tensors. And fifth point, dependent component analysis. We propose here a new approach, able to decrease the overall numerical complexity of the process by keeping low both the cost. We propose here a new approach able to decrease the overall numerical complexity of process by keeping low both the cost per iteration and the average number of iterations to reach the convergence and the same performance level that JETO and JDTM. This algorithm is called joint eigenvalue decomposition based on Taylor expansion JDTA and has been inspired by the algorithms H-nodals for JDC. Let's talk about notations. Now let's talk about notations. In this upcoming slides or upcoming topic, what all we need to go know and what are the notations of this we will be discussing here in this slide. In this paper, scalars are denoted by lowercase, vectors are vector lowercase, vectors by a lowercase boldface, and matrices by uppercase boldface. The ith element of the vector A is denoted by AI. Same-wise jth element is AJ, and I comma jth element of a matrix A is denoted by AIJ. The identity matrix is generated by I. The operator diag dot represents the diagonal built from the diagonal of the matrix argument. The operator z diag dot sets to 0 the diagonal of the matrix argument is Frobenius norm of argument matrix. The notations are completed here. Let's go to the next slide. Let's come into the main topic. A fast method for JVD based on Taylor expansion. Here we consider that all matrices are of n into n size. To solve our math problem, we have to find an estimated matrix A such that for all matrices m power k, A inverse mka are diagonally as possible. The matrix A is estimated iteratively by successive updates. At each iteration I, a matrix Bi is, is computed in order to decrease diagonalization criterion, and the matrix set is updated as for all I is equals to 1 to S, for all k is equals to 1 to k. T power k is t power k I plus 1 is equals to b inverse I t power k I bi. That's the form setup. With t power k 1 is equals to mk, S is the number of iterations to reach the convergence. Thereby, if S iterations allow to achieve the JEVD, A bar will be equal to pi of I from 1 to S bi, and all the T per Ks matrices are diagonal. To process, a classical approach is reduced at each iteration the following criterion based on quadratic measure of diagonality. The equation was given here. C of bi is equals to the equation. There's a diagonal and so on. It's given there. As said before, at each iteration we have to determine the n square of the matrix Bi. Here we simply decompose Bi as follows. Bi is equals to I of I plus Zi, where Zi is equal to Z diagonal Bi. Hence, at each iteration the updated data matrices become for all k equal to 1 to k, t power k I plus 1 is equals to I plus Zi by inverse t power k plus 1 I plus Zi, so that the criterion depends only on Zn and can be written as the follows. Down there is an equation that can be written on that way. As we said, Bi is a matrix. Here, there we simply decomposed that. In the following, to simplify the notations, we drop index I. To solve this problem, we aim to minimize the previous criterion. More precisely, an approximation of this criterion. Indeed, it is compulsory to approximate our criterion if we want to work on an analytic form of Z. For this purpose, we assume that we are close to. For this purpose, we assume that are closely to solution, so that mod of z is less than 1. Then we compute its first order Taylor expansion, which yields 1 plus z inverse t power k I plus z is equals to. By simplifying and doing the equations, we get the last equation t power k minus z t power k plus t power zk t power k z. Each matrix T power k can be decomposed as T power k is equals to A power k plus O power k, where A power k is equals to diagonal of T power k, O power k is equals to Z diagonal T power k. Once again considering that we are close to the solution, all these T power k matrices are almost diagonal or almost T power k matrices are almost diagonal, and mod of O power k is less than 1. This is second approximation gives the down one. T power k minus z t power k plus t power k z is equals to A power k plus O power k minus z A power k plus A power k z, and thus we finally resort to the following approximated JEVD criterion. C alpha the below there is there, that's the equation C alpha power into Z bracket. Now developing 11 yields, and developing that C power alpha Z, it gives m comma n from Z from 1 to n f of Z mn, where m and n are not equal. So that's the since for all m comma n fzmn is non-negative, minimizing c alpha z is equivalent to minimize all the f of z mn independently. In order to find the elements of the updating matrix Z, we'll look for the values of Z mn which annual the derivative for all m comma n. M is not equal to n. Dou f of Z mn by dou Z of mn is equals to 2 into sigma 2 into sigma k from 1 to k equal to 1 to k of O power k mn plus A power k mn minus A power k mn nn into z mn and A power k mn minus A power k nn. At last, finally, we deduce the analytical equation zmn. In that, for all mn, m is not equal to n, and there is the equation, and that's the equation we finally got to deduce. And when we go to the next slide, there will be algorithms how to do it. Let's go into the next slide to do algorithms. Algorithm number 1, let's first do it. Now when we go to algorithm 1, that's JDT algorithm. Define a stopping criterion critic. The question: define a stopping criterion critic and a maximum number of iterations x max. Now the solution goes here is initialize a bar I is equals to 1 while critic is false and I is less than or equal to s max. Do for all m is equals to 1 to n. Do for all n is equals to 1 to n. Do if m is not equal to n, then compute zmn using the equation. End if end for compute b is equals to I plus z, compute b inverse for k equal to 1 to k. Do tk is stored in b inverse tk, b is stored in t power k. End for a b is stored in a I is equals to I plus update critic end y. This is our first. So this is our first algorithm, the JDT algorithm. It's there are a few steps initializing and end for end if. That are the steps to solve this. Now let's go to the next one. Numerical value concepts complexities of JEVD algorithm. We define here the numerical complexities of an iterative algorithm as minimal number of multiplications computed by this algorithm during each iteration. According to this definition, the numerical complexity of JDT algorithm is given by, there's a follow down, there's an equation number 17. That's given, that is the equation which we wanted. This value has to be compared to the numerical complexities of references JEVD algorithms. Hence we have four equations. Equation 18 about JETO, equation 19 about SHRT, equation 20 about JDTM, equation 21 about JUST. These four are the equations. The above 71 is an equation about above one. Now we are discussing about numerical complexities of JEVD algorithm. Cost per iteration are thus dominated by term in alpha kn Parthi. Whatever the algorithm and only the value of alpha depends on the considered algorithm. It then clearly appears that only JETO can compile with JEDTE in terms of cost per iteration. However, the average number of required iterations to reach the stopping criterion varies from one algorithm to another. It's why we define the total numerical complexities as the given one. Therefore, total numerical complexities of different algorithms have to be compared empirically by means of numerical stimulations. Numerical stimulations. Matrix set to be diagnosed are created as follows. For given values of k and n, we randomly draw according to a standard normal distribution a set of diagonal matrices. Then we compute the k matrices m power k for all k equal to 1 to k. M power k is equals to ad power k a inverse by double mod of ad power k a inverse plus sigma e power k by double mod of e power k. When e power k models at a parameter sigma allows to regulate the noise power and obtain the desired signal to noise ratio SNR value, which is then defined as minus 20 log 10 sigma. In order to validate the proposed approach, we have compared the performance of JDT algorithm with those of just JDTM and JETO according to different scenarios. For each stimulation, that is each every time we vary a stimulation parameter. For each MC run, a new random matrix set is built and the three algorithms are applied to this new set. The same stopping criterion is used for all the four algorithms with E is equals to 10 power minus 6. All the algorithms are initialized with the identity matrix. At the end of each run, two indicators are computed for each algorithm along with numerical complexities. Our first indicator quantifies the relative deviation between the eigenvalues estimated by a, by a JEVD algorithm and the actual eigenvalues of matrices MK. In the same way, our second indicator quantifies the relative deviation between the estimated matrix of eigenvectors and the actual one. These indicators are denoted RD and RA respectively, are computed as follows. After removing scaling and permutation independency, where dk and dk are vectors containing actual and estimated eigenvalues of mk respectively. Finally, we resort to three criteria in order to assign algorithm performances. These are the graphs what we have given. For our first scenario, we consider set of 20 matrices size 5 varies. This one we have introduced here a new algorithm to compute the JEVD, a set of real matrices contrary to classical approach or algorithm does not resort to any sweeping procedure so that each iteration of element of matrix of eigenvectors are directly computed. Moreover, it offers similar performance than reference JEVD algorithms in terms of estimation precision of eigenvalues and vectors. Thank you one and all for this lecture.